Assalamualaikum warahmatullahi wabarakatuh. My name is Akmal Azabin Asari, AA180601. In this video, we will explain about the PID controller and the other members team is Muhammad Akizikri bin Mat Zaid, AA180441, Harith Haikal bin Hizzi, AA181801. And the last one is Muhammad Hamis Azim bin Nur Azam, AA180024. Okay, I will start first for the introduction. Okay, the ID theory explanation, I will explain about the PID controller. Okay, PID controller is short form for proportional integral derivative, which is PID. Control is the most common control algorithm used in industry and has been universally accepted in the industrial control. For popularity of PID controllers can be attributed partly to their robust performance in a wide range of operating conditions and partly to their functional simplicity, which allows engineers to operate them in a simple, straightforward manner. It is also control loop mechanism employing feedback that is widely used in industrial control system. A PID control continuously calculate an error value as the difference between a desired set point, a measure process variable which is PV, and applies a correction based on proportional, integral, and derivative terms. Okay. PID controllers are the workshop of modern process control system as they automate regulation tasks that otherwise would have to be done manually, while the proportional control mode is a main driving force in a controller. Each mode fulfills a unique function. Proportional and integral control modes are essential for most control loops, while the derivative mode is excellent for motion control. Temperature control is a typical application that uses all three control modes. Without a PID controller, manual control of water temperature is a tedious process. For example, to keep a constant temperature of water discharged from an industrial gas fire heater, an operator has to watch a temperature gauge and adjust a full gas valve accordingly. Okay, to explain how it works, we use temperature control to explain it because temperature control is a typical application that uses all three of control modes. Okay, automatic control. To automate temperature control with a PID controller, the following are required. Install an electronic temperature measurement device, automate the valve by adding an actuator, and perhaps a positioner so it can be driven electronically. And the last one, install a controller and connect it to the temperature measurement device and automate control valve. Okay, how to use it is the operator sets the PID controller sets point, which is SP, to the desired temperature, and the controller output sets the position of the control valve. The temperature measurement, called the process variable PV, is then transmitted to the PID controller, which compares it to the set point and calculates the difference or error between the two signals. Based on the error and the controller tuning point constant, the controller calculates the appropriate controller outputs to the set control valve at the correct position to keep the temperature at the set point. If the temperature rises above its set point, the controller will reduce the valve position and vice versa. Each of the controller three modes react differently to the error. The amount of response produced by each control mode is adjustable by changing the controller tuning settings. Okay, that's all from me. Thank you.
Assalamualaikum, my name is Muhammad Zikri bin Mazadi. My matrix number is AA180441. Today I want to present about the application of PID. Consider the following application for which derivative and PID controller in the industry and the domestic uses. For the first example is the furnace temperature control. Furnace typically involve heating and holding large amount of raw material at high temperature. It's commonplace for the material involved to have a large mass. As a result, is possessed in high degree of inertia. The material's temperature doesn't change quickly even when high heat is applied. This characteristic result is in a relative steady PV signal, and it allows the derivative terms to effectively correct for error without excessive change to either the CO or the FCE, such as the material that used in the furnace is plastics and metals. They will melt the material in this furnace. At the right top corner, we can see the example of the furnace that used in the industry. For the second example is the neutralization pH control. pH is widely viewed in industry as a challenge to control. For one, pH is highly nonlinear; its behavior changes from one operating range to another. For another, the buffering effect of the some material can cut what would otherwise be volatile dynamics until the buffer is saturated. While the dynamic of pH are challenging from a control perspective, they are well suited for the PID form of the controller. Specifically, the dynamic of pH tends to be slow, and the amount of caustic or acid that typically added to a process is relatively small when compared to the volume of existing liquid. The slower dynamic allows derivatives to improve control without overworking the FCE. At the bottom left corner, we can see the example of the pH neutralization reactor. This will be help to make the acidic liquid to have balanced pH and some of the low pH to high pH. This will help in industrial such as to build some material or some food. And the last example is the batch temperature control. In contrast with the furnace example mentioned above, batch temperature control is basically operate as a closed system. While bubbling and other process noise will certainly be evident in the data, noise on the whole is less of an issue in a closed system. Other aspects to batch temperature control related to temperature itself. While heat can be applied to either maintain or increase temperature, many batch temperature control processes do not include a cooling loop which with which to counter the effect of heat. Said another way, heat can be added but it can't be subtracted. The not if the net effect are dynamic which are both slow and nonlinear, and noise within the data is limited. The characteristic make for an ideal application of PID controller. For this application, we can see at the bottom left corner, there are batch temperature control that used in the food industry at the factory. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Haris Haikal Haq bin Izzir. AA 181801. Okay, I will explain the result in discussion for model 1 and model 2. Honestly, I don't know how to use Simulink model to get the value of settling time, steady state error, and overshoot. So I use coding to get those value. Okay, so here the coding num is numerator, din is denominator, GP equal to TF is is transfer function, and H equal to 1 is unity feedback, and I write type to display the state response. Okay, first we need to get the value same as the system design requirement. Okay, for model 1, when I run the coding, I got this display of state response is quite messy and full. I cannot get the value of overshoot, the value of steady state error, the value of settling time. Okay, the graph type is undamped, but I cannot get those value. Okay, when I put the PID controller here, the coding of adding the PID controller, I still cannot get the value. It's more messy and full. Okay, it's continue until we change the KD, then we change the KP, we change the KI. But here we forgot to add the result of adding KI and KD. We really sorry. Okay, for model 2, here is the Simulink model graph. When I double click the scope, it's pretty same when we choose the coding one. So here the coding I write. When I run the coding, I get this graph. The overshoot is pretty high. It's not same as the requirement, but the settling time and steady state error it's sweet with requirement, which is 3.72 seconds, less than 5 seconds, yes, and steady state error is less than 2%. So the graph type is under them. When I add the PID controller, here the coding day, I get the orange one graph, which is the PID graph. Okay, so when I change the KP, the overshoot is higher than the blue one, the graph without the PID. But the settling time and steady state error still suit with requirement. Then when I change KP to 6, it's still high, and KP equal to 9, it's still high. So when I change the KD value, I change the 2, but KP I use the best value is 6, but I change the KD first, I change 2, and here it's pretty much decreasing from the KP. It shows 7.22%, which is it suit with requirement less than 10%. And then okay, and settling time also suit. And I changed KD is 5. Okay, the overshoot decreasing. Then when I change the KD equal to 8, the overshoot still low as soon as the requirement. Okay, so from there I get the result that suit with the suit with the transfer function system design requirement. Alright, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Naim Sazim Nur Azam. I will explain about Model 3 and Model 4 result. First, Model 3. This is simulating graph. This is graph that we get with coding and full characteristic. The type of graph is underdamped. Overshoot is 69.4%. Settling time 1.87. Steady state error 0.833%. This is Model 3 with PID KP equal to 3. The overshoot is 80%. Type settling time is 1.91. Steady state error is 0.938. Next, this is Model 3 with PID KP equal to 6. The overshoot is 69.4%. Settling time is 1.93 and steady state error is 0.968. This is with KP equal to 9. The overshoot is 87.7%. Settling time is 1.91 and steady state error is 0.978%. This is Model 3 with ID that KD equal to 5. Overshoot is 2.01%. Settling time is 1.87 and steady state error is 0.78%. Next, KD equal to 7. Overshoot is 2.05%. Settling time is 1.87 and steady state error is 0.978. Last with KD equal to 10. Overshoot is 2.09%. Settling time is 1.87 and steady state error is 0.978%. So this is Model 4 without PID. We get a graph in scope. Overshoot is 209.55%. Settling time NAN. Steady state error is INF. Next, if we add PID, KP equal to 3. Overshoot is NAN. Settling time also NAN and steady state error is INF. Next, KP equal to 6. Overshoot equal to NAN. Settling time also NAN and steady state error is INF. Last for KP equal to 9. Overshoot equal to 9 and NAN. Settling time equal to NAN and steady state error equal to INF. Next, we use PID that change KD to 4. Overshoot is 21.4%. Settling time is 1.77 and steady state error is 0.968. KD equal to 7. Overshoot equal to 2.83 E plus 0.3. Settling time equal to 1.51 and steady state error is 0.968%. Next, KD equal to 10. Overshoot is 3.42 E plus 0.3. Settling time is 1.44 and steady state error is 0.968. This is table 1 that we combine all result of simulating that not at PID controller. This is table with PID that we change the KP, and this table 3 is with PID but we change KD. Thank you.